squares algorithm. And as before, before we start the actual topic for today, we have firstly some unfinished parts pertaining to the last lecture, and I would again like to begin with some doubts which were expressed at the end of the class last time. Now, last time we were actually going through the linear least square filter. And in that we had actually developed one quite interesting relation, which is that Wn plus 1 is equal to x transpose n xn whole thing inverse x transpose n dn. This is the relationship that we had got as the n plus 1th weight of the system. Now, as we discussed last time, that this is actually independent of Wn. So it doesn't. So it is not a recursive form of the expression that we are using without using Wn, we are able to use Wn plus 1, as if to say that if xn and dn, they are known to us, then we will be able to compute Wn plus 1, right. But this had raised one serious doubt at the end of the class last time, that whether we can forget about all the past observations. Is it so that it is only the present observations that we are considering? No, about dn it's okay, because dn is the expected output of the, target output of the nth observation. But this one, please note that these are capital X, okay. So some people must have wrongly thought by assuming this to be small x, and I had intentionally made one distinction between the small x vector and the capital X vector. Actually, if you remember that the capital X vector, okay, we were indicating the capital X vector for n observations as a collection of n such small vectors. So it is x1, x2, we should write it as xn should be equal to the vector that we will get out of x1, x2, so on up to xn, okay, where x1 is nothing but an m dimensional vector. So this is nothing but an m dimensional vector, which is the first observation, right. And likewise x2 will be the second observation, xn will be the nth observation, and this xn, this capital Xn matrix that we are getting effectively, in fact we are getting this, we had defined this to be this transpose, that means to say that we are going to get it as n by m dimensional matrix, okay. So those who had wrongly inferred that Wn plus 1 is only dependent upon xn is wrong, because what we mean is that here the entire x1 to xn is to be considered. So in other words, the matrix xn includes x1 to xn, okay, all these observations, and we are making a note of all these observations together in this matrix xn. So if all these things are known, then only we are able to compute Wn plus 1. So this is the idea that I wanted to convey, that in this case I mean this Wn plus 1, please remember that it is indeed dependent upon all the observations. Only thing is that in the earlier case, you remember that we were deriving Wn plus 1 in terms of Wn plus something, okay, which was in fact a recursive relationship, whereas here this converges to a single iteration, because all that we need to know is the set of xn's, the set of inputs of n observations and the nth target output, that is all, right. So, this is one of the things that we were discussing, and then towards the end of the class actually we were considering the limiting case of the linear least squares filter, okay. And as we said that in order to describe the limiting form of the linear least square filter, we had assumed that this xn and dn, they are basically taken from an ergodic process. They are basically taken from an ergodic environment. So, as I discussed in the last class, that ergodic necessarily means that it is a stationary environment, so that we will be able to obtain the expectation by averaging only one sample function in the time domain, right. So, from this consideration we said that such an environment, okay, will be described by in terms of second order statistics, where we were considering, we had defined two things. One is the correlation matrix of X, okay, which we are calling as the Rx, which is nothing but the correlation matrix, which we had defined last time as Rx being equal to the expectation of Xi matrix, I mean to say X transpose I. Okay. So, this is the correlation matrix, I mean the definition of that, and the second parameter that we had defined is the cross correlation vector, okay, between Xi and Di. So, that we were defining as Rxd, which was in fact defined as the expectation of Xi Di, right. So, this is the cross correlation, and this is the cross correlation between this Xi and the Di, right. So, now let us see that how we can express this Rx and Rxd. In fact, the correlation matrix Rx can now be expressed as follows, that Rx is expectation of Xi X transpose I, which is equal to limit of n tending to infinity. I mean this is because it is ergodic. So, we are taking n number of observations where n is sufficiently large. So, that is why we are having n tending to infinity, and what it means is that we have to sum up these. So, what are these? We have to sum it up, sum of this Xi X transpose I, okay. This we have to sum up over I is equal to 1 to n, and then we have to divide it by 1 upon n in order to get this Rx, okay. So, in fact, if we can of course take it to be, I mean by applying this definition, it is possible for us to say, I mean this is again the small x's, okay. Please remember these are the small x's. So, this is Xi. So, Xi means the m dimensional input vector. I mean Xi is the ith observation of the input vector, X transpose I is just the transpose of that Xi, okay. So, this is the ith observation, and we have got n such observations, okay. So, this in other words can be expressed as the limit n tending to infinity, and we can express it as 1 by n capital X transpose n, okay, times x n, right. So, this is what we are getting as the R x. Okay. So, this is the limiting form of the equation of R x, and the cross correlation vector, that is R x d, that can be expressed as the expectation of x I d I, which is equal to limit n tending to infinity 1 by n summation I is equal to 1 to n x I d I. Okay. Again, x I here is the small x I, okay, small x I d I, which becomes equal to limit n tending to infinity 1 by n capital X transpose n d n, right. So, this is the so these two quantities are expressed as follows, this the correlation matrix R x and the cross correlation between the x and d I, all right. And then we can formulate the linear least square solution as follows. You see, the linear least square solution as we had obtained is for W n plus 1. We are obtaining the W n plus 1th vector, right, which can be defined as the limiting vector W, where this W n plus 1 we have to compute as the limit n tends to infinity, right. So, the limiting solution of this least square problem, least square filter, is limit of W n plus 1 as n tends to infinity. Okay. And this limiting solution is also called as the Wiener solution. So, the expression that we are getting for W is the Wiener solution, and now here we can substitute the expression for W n plus 1 that we had already obtained for the linear least square filter. What is the relation that we had got? We had got these expression that W n plus 1 was equal to x transpose n x n, the whole thing inverse, times x transpose n. Okay. This itself was defined to be the pseudo inverse of x n times d n. This is what we had got as W n plus 1. So, here in place of W n plus 1 we can as well substitute that, which leads to limit n tending to infinity x transpose n x n inverse x transpose n d n, right, where it is possible to show that this can be split up into product of two limits. Okay. And what are they? This can be split up into limit n tending to infinity 1 by n x transpose n x n inverse, okay, times limit n tending to infinity 1 by n x transpose n d n. Okay. And this, by our basic definition, is the R x matrix. Okay. This is nothing but the R x matrix. So, here it becomes R x inverse. Okay. This becomes the R x inverse matrix times R x d. Okay. So, that means to say that here the Wiener solution that we are getting is a product of these two. Yes, any questions on that? 1 by n.
So we don't have it in the
Yeah? Yes, this? This is this can be actually shown that if we break it up, okay, if we break up this quantity, then there is a 1 by n square. I mean, because you see that here we are taking two products separately like this, okay. So if we break it up, then it can be shown that it is 1 by n times this, okay. Inside the bracket.
1 by n.
No, here okay, no, I mean you see, this is no, this is the basic definition of Rx, you see. So we are applying the basic definition of Rx as follows. So this whole quantity, right? So Rx is limit n tending to infinity of this entire quantity.
So if you want to write Rx inverse, then it will be n that quantity inverse.
Okay. I've got your point. Okay, you are saying that Rx inverse, yes, Rx inverse is equal to limit n tending to infinity. I apply the basic definition, that is 1 by n into x transpose n xn, the whole thing inverse. Yeah, right. So this is actually the whole thing inverse, but the question is, yeah, that becomes Rx inverse. So here, yeah, you are right. So your observation is correct that it should be 1 by n should go inside the bracket. Very correct, yes.
So this, I think this 1 by n comes up to neutralize as n and 1 by n. There is no 1 by n square term.
Because 1 by n inverse becomes n and
Yes, very correct. There is no 1 by n square term. Yes, there is no 1 by n square term. In fact, what happens is that this 1 by n goes into the inverse, and that effectively nullifies this n term. So this can be shown. I mean, we are not going into the details of the matrix manipulation, okay, but this effectively becomes the, I mean, Rxd, and this becomes the Rx inverse. Does it solve the doubt? Perfectly? Okay. Thank you very much. So now, what we are, yes, there is some afterthoughts that we should get on this, that here you see that W0 vector is equal to Rx inverse times Rxd vector, right. Now here you see that means to say that solution of this Wiener, so in order to obtain the Wiener solution, we must have a idea about this Rx inverse and Rxd, okay. But the question is that if we are knowing the statistical parameters or the statistical nature of the data beforehand, then I mean that we are in fact really going to have, that beforehand we will be knowing the correlation matrix as well as the cross correlation between the inputs and the observed outputs. So since we are not knowing that beforehand, it is not possible for us to calculate this W0 vector in such kind of environments. So in fact, for any practical purpose, that means to say for any unknown environment, we have to go in for an adaptive filtering, right. So we have to go in for what is called as adaptive filtering, and one such kind of adaptive filtering that we are going to adopt is the least mean square or in short form we are going to call it as the LMS. So, we are going to describe the LMS algorithm now. Now, LMS algorithm, mind you, has got very much similarity to the linear least square that we have formulated, but the major dissimilarity lies in the fact that in the case of linear least squares, we were taking the cost function to be the summation of all the error squares. So, the cost function CW that we were taking was actually E1 square plus E2 square up to En square, whereas in the case of least mean square we are taking only as the cost function we are taking only the instantaneous value of the error. That means to say the cost function CW calculated at W is equal to Wn is simply equal to En square, or rather half of En square, because we are all the time inserting that factor of half because of our convenience in computing the derivative. So, LMS takes the instantaneous value of the cost function. Which is CW is equal to half of En square or E square n. Okay. Now, differentiating, now if we differentiate this CW with respect to the W vector, what we get is, we get En times dou En dou W. Okay. Now, like the linear least square filter, again here we are operating with a linear neuron. So, this operates with a linear neuron, so that it is possible for us to calculate this dou En dou W easily, because we know that for a linear neuron En is equal to dn minus x transpose W, x transpose n Wn, right. So, that is why we can compute dou En dou W is equal to what? Is equal to minus x n, simply because this is x transpose. So, differentiating by the vector means it is the transpose of the transpose, and this becomes minus x n. Okay, we are differentiating with respect to W over here, and the derivative of dn with reference to W is definitely going to be 0. So, this is equal to minus x of n, so that it is possible for us to write that dou C dou W. So, we can write dou CW dou W is equal to minus En xn, right. Okay. And this this is actually the estimate of the gradient. Mind you that this is not the exact gradient, because for exact gradient we would have required the error as a vector. Okay, E1, E2 up to En we would have got, but in this case we have got only the En. Okay. So, we can express these, the derivative of C with reference to W as the gradient estimate. So, gradient estimate can now be written as, in fact, whether we write it as minus En xn or whether we write it as, because in this case En is a scalar quantity. Okay, En is equal to dn minus this. So, we are taking only one neuron. We are taking only one neuron, and this is the nth observation of that. So, En is a scalar, dn is a scalar, and this x transpose W that itself becomes a scalar, although individually x is a vector and w is a vector. Okay. So, this is simply the linear neuron model. Okay. That is what we are considering. So, this E n minus E n x n can also be written as x n E n, it does not matter. So, this is the estimate of the gradient. So, since this is estimate, we are indicating as g hat, not as g exactly. In the case of steepest gradient, we were indicating it as g n, but here we are writing it as the estimated g n. Okay. And because it is equal to minus n, I mean minus of this quantity, what is going to be our updating equation, or what is the LMS algorithm equation? In fact, are we correct in writing that W n plus 1 is equal to W n plus, because it is the gradient. So, we have to move in a direction opposite to the gradient. So, that is why it is W n plus eta x n E n, where x n E n, or eta g n or eta g n is equal to minus, g n is equal to minus x n E n. So, it becomes W n plus 1 becomes equal to W n plus eta x n E n. Okay. Is it correct? Nobody is objecting to it. Is it the same as that of the gradient descent that we have discussed? Steepest descent, steep and descent approach that we have discussed, is it same as that? Exactly same as that? It is not, because after all we have made an estimate of the gradient, and because we have made estimate of the gradient, even the weight that we are computing is also an estimated weight. So, it is not right for us to indicate this by simply putting W or W vector. We should put it as W cap vector, both for n plus 1 and n. So, W cap n plus 1 is equal to W cap n plus eta times x E n. Okay. This is our equation for the weight updating equation for the LMS algorithm. Okay. So, can we now call it, because our basic objective was to make it an adaptive filter. Now, can we call it an adaptive filter? Yes or no? Anybody disagreeing that it is not an adaptive filter? It is an adaptive filter, but why? Why is it an adaptive filter? You see, we are starting with the first observation, right? So, what is our error? Our error is E1. Okay. So, we are having half of E1 square to be our cost function. We begin with any arbitrary weight. To start with, we had W0 as the initial weight. So, we start with any arbitrary initial weight assignment W0, and first time we operate with E1, which we are getting as the difference between D1, D1 is the expected output for the first pattern, D1 minus X1 transpose W1 or W0 here, or rather to say the first one, if you are calling as 0 vector, then everything is, your D0 will be equal to, your E0 will be equal to this. So, your observations will be actually E0 onwards. Okay. W0 is the starting weight and you are getting the first error, and then based on that first error you are updating your weight, and the weights are getting updated as you are learning more and more. So, that means to say that even if the environment changes, okay, then also we are updating the weight according to the changes that we are observing in the observations. It is not that we are taking all the n observations together and then doing the updating, we are doing the updating with every observation. Okay. So, there lies one great this thing, but one thing is there, that here we are not getting the exact idea about the weight, we are getting the estimated weight. I mean, if we are comparing it with respect to the steepest descent approach. Now, one thing which we had pointed out for the case of steepest descent approach is that the steepest descent approach follows a definite trajectory. I mean, as we iteratively go on, okay, the steepest descent will follow a definite trajectory. Remember that we had illustrated that with a simple two-dimensional space where we were taking just two vectors W1 and W2, okay, and we were considering the contours like this, and then we were considering one operating point, and then it was going into the solution following a fixed trajectory. Okay. Here I mean, in that case the weight that we were obtaining were the exact weights, whereas in this case this is going to be estimated weight. So, you cannot expect I mean, as good a trajectory that you could imagine in the case of steepest descent, because what we are doing is actually an approximation to the steepest descent. So, that is why the trajectory that we will be getting is more like a random, I mean, there will be some randomness in the trajectory. Okay. So, that is why this approach, okay, which is actually in tune with the steepest descent, but not exactly the steepest descent, okay, is very often referred to as the stochastic steepest descent. So, here the very fact that we have used the word stochastic before the steepest descent means that its behavior is having some I mean deviations from the perfect steepest descent that we are going to have. So, here we will be having such kind of variations. Okay. Now, we are going to consider the convergence aspect of this LMS algorithm, but before we go into that, I mean, let me again invite some questions from the participants here. Any questions? Okay. So, we go over to the convergence consideration. Now, one point that we note here is you see that the equation that we had obtained is Wn plus 1 or W cap, in fact W cap n plus 1 is equal to W cap n plus eta of this term. Okay. And what is after all eta of this term? Okay. It is dependent on En, okay, and En is nothing but Dn minus Xn Wn. Okay. So, in other words, the weight that we are getting is following some dependence on the Xn and Dn. Okay. Now, in this case, one thing that we should consider is that of course, and I mean first and foremost it very much depends upon this eta. Okay. So, that is why any convergence criteria. So, if we fix up this Xn, for example, okay, if we fix up this En, okay, that means to say that we fix up the environment, then the Ens are also fixed up, because Ens then will depend only upon the weight, because if Xns are fixed, then likewise the Dns are also fixed. I mean, if you are fixing the patterns, then their expected outputs are also fixed. So, that is why the Ens that you are getting is only dependent on weight. So, in other words, we can say that the weight updating equation will be dependent upon eta only. I mean, for fixed n, I mean for fixed set of inputs, the weight updating equation will very much depend upon eta. And as we discussed before, that from all practical and convergence criterias, we have to take very small values of eta. Okay. It is a must that we have to take very small etas. Now, what are the convergence considerations that we are going to take? Okay. The first criteria that we normally take is the convergence of the mean. Okay. Convergence of the mean, and this is described as the expectation of Wn. Okay. Expectation of W cap n, in fact. Okay. In fact, as n tends to infinity, I mean if we make the number of observations to be large, okay, then I mean what is it that it's going to be? What can you expect to be the expectation of Wn? Equal to W naught. Yes, you can expect it to be W naught, which is the Wiener solution. So, expectation of Wn is I mean tends to W naught as n tends to infinity. Okay. But this is of little practical value, okay, since a sequence of 0 mean but otherwise arbitrary random vector, okay, can also converge in this sense. Okay. And from a practical point of view, a better convergence criteria that we normally see is that the expectation of its squared error, okay, that means to say E of E square n, that becomes constant, okay, as n tends to infinity. Okay. So, in other words, that if it becomes, if the expectation of the error that becomes constant as n tends to infinity, then also we can say that the LMS algorithm has converged. Yes or no? We can say that because I mean if the error, I mean if there is no change in the error, if it has already gone into a constant error with iterations, okay, that means to say that its characteristic is something like this, okay, where this is the, I mean if this is the error or the cost function, then the cost function will get a fixed value here. So, this thing is a constant is a good measure that it has actually converged. So, for all practical consideration, we will be taking the convergence of the error, convergence of error to be, I mean convergence of mean square error, okay, as the LMS algorithm's convergence consideration. Okay. In fact, I mean the convergence analysis is very much detailed, I mean involves quite complicated mathematics. So, that is why people have solved this problem only under some assumptions, and those assumptions, mind you, are more or less reasonable assumptions. And what are the assumptions that people have adopted to solve the convergence problem? So, assumptions made in showing the mean square convergence criteria. Is, I mean number one assumption is that this x1, I mean the small x1, x2, okay, up to xn, okay, they are all statistically independent. So, all the observations that you are having, I mean all the inputs that you are having, they are statistically independent inputs. Okay. The second assumption is that the input xn, I mean the nth input xn, okay, is independent. I mean here all these x's are the small x, okay, please do not feel confused. So, this xn, the nth x, that means to say, is independent of di, where I is equal to 1, 2 up to n minus 1. That means to say that the nth input is independent of the previous target outputs. Okay. Not unreasonable to assume that. Okay. The third consideration is that although dn is dependent on xn very much, dn has to depend upon xn, but dn is independent of d1, d2 up to dn minus 1. Independent of di, I is equal to 1 to n minus 1. Okay. The fourth assumption is that this xn and dn, they are picked up from a Gaussian distribution. Because unless the distribution is assumed, unless the distribution of this xn's are assumed in some form, okay, it is not possible to show the convergence criteria. So, the convergence criteria can be shown only under some distribution, and in absence of any definite knowledge about the exact distribution, I mean it is not unreasonable to assume that xn and dn will follow a Gaussian distribution. So, we pick up the xn and dn out of a Gaussian distributed variable. So, now if we assume these four things, then it can be shown that the LMS algorithm converges in the mean square error sense. If these four are valid, then the LMS algorithm converges in the mean square error sense, and this has been actually shown by Heikin. Okay. And Heikin has shown that under these assumptions, under these four assumptions, right, the LMS algorithm is convergent in the mean square sense, provided that the value of eta lies within 2 and lambda max, I mean within 0 and 2 by lambda max, where lambda max is the largest eigenvalue of the Rx matrix. So, it is the largest eigenvalue of the correlation matrix. Okay. Now, in a typical application, actually the idea of this lambda max is not available. Okay. And in such kind of cases where the lambda max is not available, then a more conservative estimate about this eta, more conservative estimate that one can have is more conservative estimate when this lambda max is not known, is simply by looking at the trace of the matrix Rx. Okay. If you are taking the trace of that matrix Rx, that can be approximated for lambda max. So, a more conservative estimate for eta is where eta lies between 2 and I mean 0 and 2 by trace of Rx. Okay. And what is the trace of Rx? What is the significance of the trace of Rx? Sum of the diagonal elements. Yes, very good. So, that is the sum of the diagonal elements. And what are the diagonal elements signifying in the case of the correlation matrix? Yes, the power terms. Power terms means the mean square values of the sensor inputs, because after all we have got the Rx matrix as the expectation of capital X transpose capital X. And what was capital X? Capital X was nothing but the matrix that we had formed out of the input vectors x1 to xn. Okay. So, that was actually composing the big X matrix, and that big X matrix that we had got, okay, its diagonal elements will be having all the x1 squared term, x2 squared term, x3 squared term up to xn squared term. Okay. So, the trace of the matrix in fact will be indicating the mean square values of the sensor input. So, what we will be getting is that the value of eta should lie between 0 and 2 by the summation of mean square values of the sensor input. Okay. So, you can see that for all practical consideration, the convergence that Heikin has shown under all this assumption, okay, basically says that it is convergent in the mean square error sense only when the value of eta is within this, or a more conservative estimate would say that within this. So, this is very easy to compute because we know that what our inputs are, okay, and if we know that what the inputs are, we simply add up the inputs, okay, thus the square of those inputs, okay, and we sum it up. Of course, we have to make large number of observations on that, and then if we have 2 by that quantity, okay, that will give us the upper limit of eta, okay, and if eta is restricted to this bounds, okay, then the convergence of the LMS algorithm is guaranteed. Okay. So, this is in fact any large values of eta obviously will make the system unstable, because this aspect we discussed earlier also, that the convergence will be only restricted for the case of the smaller etas. Now, another consideration that we should have is you see that, let us go back again to this equation, that Wn plus 1 is equal to Wn plus eta times xn en. Now, what is the effect of small eta and what is the effect of large eta on the learning itself? Okay. Now, if you are having a small value of eta, okay, then obviously one point is there that it learns slowly. Okay. But when it learns, okay, it learns all the inputs that have been presented so far, mind you, because we are iterating upon this algorithm for n equal to 1, 2, etc., right. So, every time we are making contributions, okay, which are getting embedded. So, what happens is that when we compute Wn plus this quantity, first time it does this incremental learning and gets into this updated Wn plus 1, then this Wn plus 1 is already containing, okay, this Wn plus 1 will be used in the next iteration in place of Wn, all right. That means to say that it has already learned the first one, okay. Now, if eta is small, then another small incremental learning is added to it, so that in the end this Wn will contain the learning that has been contributed from everything. Whereas, if the value of eta is quite large, then what happens? Then what happens is that as compared to Wn, this term will contribute more. That means to say the current input that you are providing is contributing more to the learning rather than the agglomerated effect of all the past inputs. So, a small eta makes a contribution of all the inputs that we have presented so far, whereas a large eta means that it gives more biasedness towards the input that is presented at the last time. Okay. So, that is why from a memory point of view, from a system memory consideration, we should say that a system that is having smaller values of eta has got better memory as compared to the systems which are having larger values of eta. Okay. So, it is not only the convergence criteria, but even the learning also is better. But only thing is that a small eta, the price we pay for a small eta is nothing but the slower convergence, that is all. Otherwise, we are gainer. All right. So, in fact, I mean, coming to the pros and cons of the least mean square approach, we can say that least mean square approach is definitely a very effective linear adaptive filter. Okay. There cannot be any doubt about it, and it is so simple to implement because its cost function is just formulated as the instantaneous error square term. Okay. And the only price that we pay for in the least mean square algorithm is the slow convergence. Any questions? Okay then, thank you.